So welcome everyone. Thank you all for coming. Thank you all the members of the jury for accepting being here in the thesis defense of Daniel Tandeitnik. Thank you also all the people that are here. There's some audience, live audience that is watching this. So now Daniel will present his work. Daniel, you have about 50 minutes, and then we will start the discussion with the jury members. If anybody has a question, of course, feel free to ask. And then we will go to the questions where everybody will ask Daniel about his thesis, and then we will discuss the result. So, okay, thank you very much. Daniel, you can start.
Okay, hello everyone. My name is Daniel Tandeitnik. I'm a master graduate student here at Rio, and I was advised by Thiago Guerreiro, and I'm now too his PhD student, so there's a lot of trust between us. This is my thesis presentation, my master thesis presentation. Thanks to all for coming, and I hope you enjoy what I'm going to show you guys. So, c'est parti. Originally, I was meant to work at the lab, like doing some levitating nano-sized particles in vacuum, but along came the epidemic, so I had to change what I was doing. I wasn't able to do experimental work. And one day at the lab, I was chit-chatting with Thiago and about life, the universe, and everything else. And it came the idea, what if we can we employ the mechanisms of natural evolution to evolve mathematical solutions, specifically solutions to quantum mechanics and quantum computation? If we are clever enough, can we evolve quantum secrets? So this is what we did on my master. So to answer this question, I will follow this line. And I hope I will show you guys that, yes, we can evolve quantum error correction codes, we can evolve quantum circuits using evolution. So let me put a pointer here. So I hope to show you guys how I can take the concept of natural evolution, adapt it into a computer algorithm, so it can evolve quantum error correction codes. And in the end, I'll show some future developments of what I did, so future evidence I can go. So first things first, evolution in the mathematical point of view is an optimization process, where this is a classical example. This is the Darwin's finch that he studied at Galapagos. So the basic is you start with an initial population, like this bird with a standard beak that is not specialized to do nothing in particular. So maybe it will be isolated on an island where it only has like hard fruit to eat. And through the evolutionary process of selection, reproduction, mutation, competition, after many generations, its beak is going to change and become optimized, like to eat hard fruit, or to eat larvae, or to eat bugs. So, in a mathematical point of view, evolution is to optimize some feature of the animal, the living organism. We can visualize this process as this fitness landscape that is drawn here. So we can think that the environment defines a reproduction rate that is function of the characteristics of really useful to visualize it like that. And of course, Kaufman here in the audience, he made such a model on type of the NK model in the 80s, and it was very famous. And it's a kind of fitness landscape too. And here you can clearly see that I copied his drawing, but it's the same idea.
Stu, you are on mute. Sorry,
Say something.
if you wanted to say something.
I just wanted to say thank you, Daniel.
You're welcome.
I just wanted to tell you, one time I was introduced as the grandfather of a domain of science. I wanted to be the father, but grandfather, gosh. Anyway, go ahead. This is all great.
Thanks. So it's not new to humans to want to emulate natural selection and evolution. We've been doing that for millennia through breeding selection. Like for at least 5 millennia, we domesticated wolves and transformed the wolf into the dogs we have today. We transformed the chicken that today they call the Frankenstein chicken, that is enormous through breeding selection. Corn, there's a lot of examples. So it's not new for humans to try to emulate natural selection. So it's natural when computers came about to try to emulate with computer algorithms. So if we can make it with animals, can we make it use the ideas of evolution to evolve solutions for mathematical problems? So this is not a new idea. This began at the 50s, 1957 to be exactly. And it is a really active research field. So this in my drawing, I want to show that it's really active. There's hundreds and thousands of papers using the technique of what they call the evolutionary algorithms in many fields to solve mathematical problems that can be written as an optimization problem. So how do we adapt natural evolution into a computer algorithm, especially to evolve quantum circuits? That I'm going to specialize in that, of course. So in biology, what we do, you have individuals that we can think of as DNAs. I have in this work, I have a genetic point of view of evolution. So we have the individuals that are DNA. I abstract the DNA to the genotype. That is a sequence of nucleotides. And the important thing when I do this abstraction is that the nucleotides the structure is modular. So it's always repeating sequence of A, C, T, G. So it's like a Lego that I can build. And from the genotype is mapped into the phenotype of the animal. In this case, I put here two morphs. One morph, the phenotype is the characteristics the final individual show when it's born. Here we have so it can be the color, the wingspan, in the morph case, and other characteristics. And here the most obvious one is the color of the morph. Here we have a black morph, and here we have a white morph. So genotypes are mapped into phenotypes, and the phenotype plus the environment is what makes the selection. So here, I don't know if you can see, but this is a bark of a tree. You have the black moth, and I don't know if you can see there's the white moth. There's a white moth right here. It's really well hidden with its color. So we have the environment is the bark of the tree, and it's the bird that can see some colors and some colors variation. So here, the bird can see the black moth, but it can see the white moth. And as a consequence, the black moth is eaten in this scenario. So it's selected to be eaten, it dies. And the white moth, it survives, it's lucky, and it can breed at some later point, transmitting its genes for the future generations that will also have the white characteristic of the skin, the pigmentation. So now we bring this idea to the quantum computation side. So we abstract circuits, quantum circuits, as a genotype. So here are two examples of quantum circuits, just two random examples. And I abstract it as this list, this matrix of the gates and the qubits the gates are affect, right? So it's just like the DNA strand that I could write it as a string, but here I write it as a two-dimensional object because I also need the information of the qubits. So I abstract circuits into this matrix, and they are two mapped into characteristics of the circuit that I also can call the phenotype of the circuit. So I interchangeably use the jargon from the biology for quantum mechanics or quantum computation. So here some characteristics of the circuit can be the depth of the circuit, the mean entropy, the corrigibility degree. In later slides, I will explain some of them. But just for now, we have this mapping of the circuit to the genotype to some characteristics. So similarly, the phenotype plus the specifics of the problem that I want to solve. So the specifics of the problem are the environment here, performs the selection. So here, as an example, you might imagine that in my problem, I want to minimize the depth of the circuit. The depth is just a measure of how long the circuit is. So this circuit has depth 3, this circuit has depth 2. So I define a fitness function, this fitness function F. By convention, I always want to maximize the fitness function. That's why I use the inverse of the depth. So if I want to minimize the depth, I want the inverse of the depth to be the maximum possible. This guy here is 1/3, this guy is 1/2. So this guy, the circuit is better in the point of view of this fitness function. So this circuit is eliminated, this is selected. So this is how we do selection for circuits, quantum circuits. So now bringing back this idea of the fitness landscape, because here the populations, they walk through the landscape. But how is this walk? It's a stochastic walk, but what makes the populations climb towards the peak? So there are two, in the biology side, there are two genetic operators. One genetic operator is a crossover operator. That's when in sexual reproduction, when two parents breed, their DNA is recombined and mixed. So like this is the DNA from one parent, it's for the other parent, and when they reproduce, their DNA mix, and this so good genes are disseminated through the population through crossover. And another genetic operator is really important is the mutation operator, because the mutation operator that brings errors to when the DNA strand is copied. Maybe some genes are copied with an error, or a new gene appears. The mutation is important so that new genes combinations can appear in the population. So these two operators allow the population to walk through the fitness landscape, and they drift towards the peaks because of the selection. The selection drifts towards the peaks, and they walk because of the genetic operators. So two are going to bring these ideas to quantum circuits, because I also need them to walk the fitness landscape of the problem that I will define. So here I have the crossover version for the quantum circuits. So it's really similar because when I define the secrets as a matrix, so crossovers and mutations will naturally become row operations. So when I select two circuits to breed, reproduce, a crossover is just I pick one circuit, I randomly choose one place to cut the circuit. I do the same thing with the other parent. So I cut them and rearrange them, stitch them together, the parts, right? Here I form two offsprings. These offsprings get this part, and these offsprings get this part and this part. So at each reproduction moment, two parents form two offsprings. And this is by conventions. It's this convention that I made. And mutation is also really simple with this convention, this matrix representation. Just I randomly choose some gates to change. And after I choose some gates, I randomly choose what I'm going to do with these gates. So like this gate this phase gate transform into a Hadamard, the Qubit Gen 2. Here I introduce a new gate. So it's really simple how to do crossovers and mutations with this representation. So now I'm going to put all together. This is again the biological evolutionary process. So this, in our genetic algorithm to evolve quantum secrets, will become this. This is the process flow of our genetic algorithm. This is the algorithm. And it's the same idea. I will have an initial population of circuits. I will make them go through this algorithm many times. Each time they go through this algorithm, it marks a generation. And after many generations, I hope that a solution that is optimized to the problem emerges. So now I'm going to talk about each process in more detail. So at the start, I initialize with a random population. So it's really random. I don't start with circuits that have some kind of bias towards a solution. So in this example, I initialize with 6 random circuits, and each circuit I measure the fitness. So here I just put some numbers. So some are better than others, right? And the first thing they do, I need to make a breeding selection. The breeding selection is really simple. I use this roulette wheel selection scheme. It's just like the probability of one of the circuits to be chosen is proportional to their relative fitness to the fitness of the whole population. So the secret 2 has a better chance to be selected than secret 1 because it has a higher fitness and so on. So I get population, I will use a roulette wheel selection. So in this example, 2 individuals are selected to breed. So I choose the randomness chose secret 2 and secret 6. It's not always the best circuits that are selected because there is a stochastic is random. So here, this guy is not the second best. And selecting 2 secrets to breed, the next part is I make the crossover. So secret 2 is parent A, secret 6 is parent B. So I make the crossover like just as I explained in some slides earlier. This forms 2 new circuits, offspring A and offspring B, circuit 7 and 8. Each circuit suffers a mutation to a random mutation that I will make a random selection, and they will transform in the final individual. And after they are in their final form, I measure their fitness. So in this case, offspring A is better than both the parents, and offspring B is worse of both the parents. We don't know what's going to happen when we make these things. And I pick these 2 new circuits and insert again into the population. So And if something I do to manage memory, or is common with genetic algorithms, I establish a population limit, a population size limit. My population have, like this is 6, my population limit. And if the population limit is higher, if the population size is higher than the limit, I purge the least fit ones. So secret 3 is purged and secret 8 is purged, and my population is resized, but the overall fitness has increased in this step. And before making the loop again, I ask if I want to halt the algorithm. So the halt, what are the halt conditions that can be? I can establish like a maximum number of generations. So I can say that I just want to give 5,000 generations, 10,000 generations, or 5,000 iterations. Now each iteration is a generation. Or if a solution was found, I know if a solution was found if I know a priori the fitness of the best solution that I can find. This can be the case. Or maybe the population diversity didn't change for many generations. So probably I'm stuck on a local maximum of the fitness landscape and I can't get out of it. So this can happen. And so you just stop the run and try again and hope not to hit that maximum again. Okay, now I established the algorithm, the genetic algorithm, but I need to specialize it to evolve quantum error correction codes, because this is my main objective. So what do I have to do? So what's my motivation to evolve quantum error correction codes? First, we don't have access to full-fledged quantum computers. Unfortunately, here at Cook Hill, we don't have one yet, right? So, but there's a theorem, the Boltzmann-Kinneal theorem, that shows that for a certain class of quantum states, we can efficiently simulate them on classical computers. When I say efficiently simulate them, I mean in a polynomial time. So I can use these states, they are stabilized states, and I can use my computer, for example. But stabilized states was created by Boltzmann, especially they are like the main language of quantum error correction codes. They were created to describe quantum error correction codes. So if you're going to work with stabilizers, it's really natural to try to evolve quantum error correction codes. So this is the train of thought that led us to evolve them. So I'll stop saying quantum error correction codes. I'm going to say QECCs for short. So just really quickly, what's the stabilizer formalism in a nutshell? The idea is that you're not going to represent the quantum state as a decomposition into a basis, like we normally do on quantum mechanics. We are going to represent them by their symmetry group. So it's an idea from group theory. In what is the symmetry group that we are going to use to represent them? Is the group of symmetries under the group of unitaries under which the states are eigenstates with eigenvalue 1. So for this unitary here, this state is an eigenstate with eigenvalue 1. Plus 1, the global phase is really important for stabilized formalism, which is normally is not important in quantum physics, but here quantum mechanics, but here is the global phase is important. So instead of representing by this decomposition, we represent it by the group formed by their stabilizers. We call these guys stabilizers, and we say that the state is stabilized by them. And we can do that because one of the things that we show in the theorem that the groups are only equal if the states are equal. So this is a good representation for the state. There's a bijection between the group and the state. And so what we do, imagine that we have some initial state that goes under an evolution. Here the evolution is this unitary U, for example. If G stabilize the initial state, so U, GU, diagram here, will stabilize the evolved state. It is really easy to prove, it's just this line of math here. So we can keep track of the evolution of the states by evaluating how each element of the stabilized group evolves. And we don't need to evaluate for every element of the group, because one result of group theory is that we can represent a group by their generators. So we don't even need to, we just need to evaluate for a smaller subset of the group, some set of generators. And there's a set of gates here, I mean, evolutions the state can go through, that when we make this conjugation operation, they conjugate into a really simple form, or more precisely, Pauli letters are mapped into single products of Pauli letters. And since we are dealing here with qubits, any operator that acts on qubits can be decomposed on Pauli operators plus identity. So what are these gates? Is the Hadamard, the phase gate, and the CNOT gate. These gates receive a special name. They're called Clifford gates. And here is the operators and how they are after the conjugation. You can see that they are all mapped to single products. And the main takeaway of the history is that we can get a circuit like this that will act upon this initial state, and we can represent this initial state by a set of generators. These are the generators for this guy, each row. And we can use these transformation rules to see how these generators transforms as we apply the gates. So here, after we apply the Hadamard gate, here after we apply the CNOT gate, and since they translate into single product of Pauli letters, they always stay confined by this shape. So we can encode these states with 2n squared plus n bits of information. So this is polynomial with n. It does not scale with 2 to the n. And what saves quantum computation for being simulated by any classical computer? It lacks one gate here to make this set universal. Is the T gate. The T gate doesn't map, does not map single Pauli letters into single products. So this saves quantum computation from being simulated on classical computers. Now, stabilizer quantum correction codes in a nutshell. So this is the general scheme of quantum correction code, a stabilizer QCC. So in the first stage, I start with a data. What's the objective of my quantum correction code? I have some state that I can call the data state or something like that I wish to protect against a list of errors that I think it may be subjective. when I do my calculations. So the first thing I need to do is to encode it into a logical state. That's the first step, where I get my data state. I pass it through an encoding circuit, and it transforms into a logical state. So I have this mapping of the data space into a code space, where my Hilbert space is enlarged. For example, I place here a simple example, the 3-qubit encoding circuit. So we start here with our normal qubit state, and after it passes through the circuit, it is mapped into this logical state, where these guys here are my code words. So I can say that what the circuit do is map the basis states of my data space into basis states of a code word of a code space. And my logical state will live in the subspace spawned by this base here. Next, we think that some error occurs because the system is always prone to have errors. Here, you consider single Pauli operators as errors because an operator can be written as a decomposition of them. And in the final state, that's where all the magic happens. I do some clever measurements here, what we call the syndrome extraction. And with the outcome of the measurement, I can, if my code is good, I can deduce which error occurred with the result of this measurement. I'm not going to get into the details of the measurement, but in the end, what we have is a syndrome table. This is the example of syndrome table for the 3-qubit encoding circuit that relates each error with a binary code. So the result of this measurement will give me some code. For example, I measure 1, 0. So I look at this table and 1, 0 means that an X error occurred at the first qubit. So if I know that this error occurred, I can prescribe the right correction. In this case, the right correction is just to apply another X at qubit 1 because these errors are unitary or reversible. Okay. So we then focus on the question. Given on the appropriate fitness function, if you can create an appropriate fitness function, can a genetic algorithm evolve quantum error correction codes? Can we create this fitness function? But first thing, what are we going to evolve on the genetic algorithm? We know we are going to evolve some quantum circuits. So if you look at the scheme, the general scheme of the quantum error correction code, the natural candidate to be evolved is the encoding circuit. Like when you study Shor's code, you study the encoding circuit of the Shor's code or the Codewords. So this is the mathematical object that we're going to evolve. Is our genetic algorithm individual. So our fitness function will depend on 3 phenotypes, 3 characteristics of the individual, the encoding circuit. Is the encoder circuit depth, the distance between the code words they encode, and the corrigibility degree. So first, the encoding circuit depth, the depth of the circuit. It's just the depth of a circuit is just the longest path you need to take to execute the circuit. I just put some example here. So in this circuit, the longest path we need to take to execute the circuit is this one that I marked. And if you count the gates in this path, you're going to count 8 gates. So the minimal time I have to expend to execute this circuit is the time I need to execute 8 gates. The depth is a measure of how complex is the circuit, or how long it takes me to execute it. So I want to minimize circuit depth. We don't want complex circuits. We want the simple circuits we can find. Next is the distance between codewords. So the encoder circuit will map the basis of the data space into some codewords. So we have something like this. This is just the abstraction of the 0 logical codeword and the 1 logical codeword. And there are two kinds of errors that can occur to the encoded state that are not correctable. You can correct them. They are the logical bit flip and the logical phase flip. Here is the logical bit flip. So 0 becomes 1 and 1 becomes 0. So it flips the codes, one code word into another code word. And the other error is the phase flip, which gives a relative phase between code words. So here I got a relative phase between them. These two errors, I can correct them because the final state lives in the code space. So the distance between the code words is just the shortest logical error I can apply to one of them to some of these cases to happen. Phase flip or bit flip, either one of them. The shortest logical error that exists is the distance. Shortest, I mean how many qubits you have to apply an operator. And finally, the accordability degree. This is something I made up for the dissertation. These other two, they are standard, but this I invented. The accordability degree, as the name says, it just measures the percentage of correctable errors, because when you establish an error correction code, one thing that you have to fix is which errors you want to be able to correct. Normally, we say that we want to correct all single qubit errors. So this is, we establish a set of errors that we wish to correct. Because as I will show, there are some errors that may be undetectable and some errors that may be uncorrectable. If our code is good, this is equal to 0, this is equal to 0, and the correctability degree will be 1. But if these errors are not 0, it will be less than 1, so it measures the percentage of correctable errors. So what are the undetectable errors and uncorrectable errors? Here we have an example of undetectable errors. Again, I use the 3-qubit encoder circuit as an example. This is the syndrome table for it again. So here, if you look at the errors, the Z-type errors, they all have the same syndrome of 0, 0. But this is the syndrome you get if no error occurred or the identity occurred. So if a Z error occurs, it will give a 0, 0 syndrome, and you won't know if any error occurred. So this is why I call them undetectable. They will occur, and you can't know that they occurred, that they happened. So how do I measure undetectable errors? I simply make the syndrome table and I count how many lines return 0. So here I have 3 undetectable errors. So regarding these these 6 errors, 3 are undetectable. So the correlability degree would be 3/6, so 1/2. And uncorrectable errors, I use the same example, but I extended the errors I'm considering to consider 2 errors on 2 qubits, X errors on 2 qubits and 3 qubits. If you check here, when I have an error on the first, an X error on the first qubit, and I have on the second and third qubit 2, I get the same syndrome. So there's a degeneracy on the syndrome. These 2 errors get the same syndrome of 1, 0. So why they are uncorrectable? Because if I measure 1, 0, I don't know if this error happened, or this error happened. And if this one happened, and if I try correcting for this error here, I will get a logical phase, a bit flip, and vice versa. So here, only half of the times I will get the right correction, the right prescription. So they are uncorrectable. So this is the fitness function, functional form that we made. Here are the depth, the distance, and the correlability degree. This form was made after many trials and errors. So here we want to minimize the depth, maximize the distance. We want to maximize the distance, so it's harder to make a logical error. And here I summed with this guy, the correlability degree is a number between 0 and 1. So I summed with 1 to get a number greater than 1, and I put it with a power of 10. So this term is more important than these other terms. Little changes here are more important than changes here, because when we were testing the algorithm, we saw that sometimes circuits with low depth came about with low correlability degree, because a change here was greater than a change here for the fitness function. So in the end, I put a 10 there, so the algorithm puts more weight on the correlability degree, because it's more important to us. So I'm really happy to show the results we got. Here we compared the performance of the genetic algorithm against a random search. So in green we have genetic algorithm, in blue random search. Random search is just an algorithm that generates random solutions and see the best solution it can get in some generations. So I'm really happy to show the results, because they are really good. The genetic algorithm, it converged to the solution really quickly. In all our tests, we tested beginning with n equals 5 until n equals 10. N is the qubit overhead of the code, how many qubits. I did the size of the Hilbert space, right? How many qubits I'm using. And on the n equals 5 case, the perfect code is a famous code, appeared always, because it's the only code with n equals 5 qubits, so it's always going to be the perfect code. And for n equals 9, Shor's code, the most famous one, the textbook example, appeared many times and many times. So in less than 1,000 generations, like less than 500 generations, the genetic algorithm, starting from random circuits, it generated Shor's algorithm, just following that the the process flow and using the fitness function that I defined. So it's really remarkable, right? And something curious happened. If you check here for n equals 6, 7, and 8, the performance of the random search increased. And for n equals 9, there was n equals 10, it started to decrease again. So I was curious what happened here, because if you recall, if you read the papers and the literature, the number of stabilized states scales with 2 to the n to the square of n. So it grows really fast. So we anticipate it to be harder to find codes as we increase n. However, we also know that the number of potential solutions also grows with n. So here I gave an example that this is a solution, this is source code. And if I swap registers, I permutate registers, this too is an example of Shor's algorithm. In this kind of liberty, this freedom, this grows if is factorial because it's a permutation. So too, the solutions also grow, but at some point, the number of states, it grows faster than the number of these freedoms. So that's why they start to rise and then they fall. And you can see this in this table, because I forgot to mention each line of that is an average over 100 trials of the genetic algorithm and 100 trials of random search. So it's an average, and it shows the best fitness it can get at each generation. So here in 100 runs, the genetic algorithm always found a solution. In the random search, RS, found a solution sometimes. It increasingly found solutions until n equals 7, and for n equals 8 through 10, it started to decline and find less solutions. So you can see here it's rise and fall. And if you consider codes with distance greater than 3, the genetic algorithm found many solutions with distance greater than 3. That's really cool, because normally we don't talk about secret quantum error correction codes with distance greater than 3. And random search just found once a solution like that. Moreover, the genetic algorithm was capable of found new interesting codes, like these 2 examples of codes. This one is for n equals 9, this one is for n equals 10, and both of them have distance 5. So what this means? This means that there are solutions, content solutions out there to be found, and the genetic algorithm can find these solutions. And maybe we can tweak the fitness function to drive it towards solutions like that and with other characteristics. So now I'm going to end my presentation talking about what's the outlook. I showed you guys that, yes, we can evolve quantum error correction codes using quantum algorithms. So what's the outlook? What's the future? What we can do now? And we have 3 perspectives, but we are sure that there are a lot more out of it, if you think. So first proposition, I showed in the dissertation that I could evolve the triangular 7-qubit color code. But I kind of cheated on the dissertation, because how I did that? I evolved them built-in on the fitness function, a term that measured how a circuit was good at being a CSS code, because these codes, they pertain to this class called CSS codes. But as Thiago, he likes to say, we didn't get the problem by default. Getting the problem by default here, the problem is to search for topological codes, is to input in the fitness function some phenotype that measures topological characteristics. We think that is possible. We are kind of stuck on this, but we think that if we can study more about topological codes and think a little more, we can specialize the fitness function to evolve topological codes. And our dream is to evolve like Kitaev's toric code and things like that. Next is the research area of quantum algorithm compilation. Is a really hot area. I made this search in Google Scholar for how many times the term quantum compiling appeared in articles. So it's in the last 3 years, it grew exponentially because new quantum computers appears every time. Quantum compilation is the problem that you want to take in unitary and approximate it by a set of gates that approximated really well, and we want to use the least amount of gates. We want the depth to be minimal as possible. And there's a theorem called the Kitaev-Solvay theorem that say that this is possible. And we think that the genetic algorithm is a really good platform to do that, because we showed that it can diminish the depth of circuits. So we think that we can take a circuit that will be our target, or a unitary that will be our target, and we can use it in the fitness function, some kind of measure of fidelity or something like that, or in a product, and use the depth, again, the inverse of the depth, and maybe we can make a quantum compilation using a genetic algorithm. And finally, the last direction that I think we can go is the production of tailor-made algorithms. I'll expand with 2 examples. First is the example on the right. Each one of these lattices is IBM's in quantum computer from IBM. The lattice for it. It shows how the qubits are connected. So which qubit can interact with each qubit. So the idea is that we can input on the fitness function some kind of measurement that penalize circuits that don't comply with the given lattice you give them. So you can give me like this lattice and ask me, find a quantum error correction code that satisfies these connections. So I can input the hardware specification into the fitness function, and it will only involve circuits which comply. So they are tailor-made for this hardware. And 2, there's this really interesting paper by Brown and Susskind called The Complexity Geometry of the Single Qubit. And what Susskind does in this paper, he defines a measure of how difficult or how complex it is to apply a certain unitary. Because it's like, imagine you have an experiment set up with superconducting qubits, and maybe to apply a Z operator on a qubit is much harder than applying an X or an Y operator, because of how the qubits are set up. So you can, in this model, you can input this information and say that the Z operator is harder, so it's more complex, and get a measure of how difficult it is to apply a circuit. So we can directly apply this result into a fitness function to make a tailor-made algorithm to in hardware with certain characteristics. That you measure how hard it is to apply the circuit using his measure of Susskind measure of complexity. So this is my final thoughts. As quantum computers improve with countless qubits in ever larger and more complex topologies, genetic algorithms may yet prove to be an invaluable optimization method in the quantum computing engineer's toolbox. We're really thrilled with the results we got. We didn't expect them like 1 year ago, and we really think that
Eve, I can't talk right now. Can I call you in about an hour?
So thank you all for attending and seeing my presentation. And I'm open for questions.
Okay, thank you, Daniel. Can everybody hear me okay? Are you guys hearing me? Because I'm using...
Yes, I can.
Okay, perfect. So now we go on to the main part of the defense, which is the questions. I am having a hard time because there is this tradition that we have to start with the member of the jury who is furthest away from us, no? And I don't know really if Santa Fe is further away from Portugal. But I remember that going to that part of the States took me a lot more than going to Portugal. So I think we are going to start with Stuart. So please do. You can ask questions, make comments, say whatever.
Well, I'm glad to. Daniel, that's really lovely. I understand the beginning part very, very well, and the latter part less well, but just delighted to see it. So I would like to ask some questions that have to do with general issues about searches on landscapes. So I'd like to mention some things to you and tell me if you think they might be useful, okay?
Okay.
So there's old literature that has been, a lot of people have contributed to it. So you have some fitness landscape, we all do. So you have some fitness landscape, and it has the property that it has some number of local peaks and some global peak. And there's a correlation structure on that landscape. Do you know about this? You walk randomly across the landscape, measure the fitness value as you walk, and then do the autocorrelation function. And that tells you about the correlation length on the landscape. And when it drops to 1/E, that's a good guess at the distance between peaks. Okay, so hold that. There's a lot of work going back years that asks about the two operators, mutation and recombination. It turns out recombination is useless on very rugged landscapes. So you're just wasting your time. So it may be worthwhile in general to understand something about the structure of the landscapes that you're searching. So you can try to pick which operators you use. Another big issue that comes up all the time, it's right there in the image that you've got. If you start at some average spot on the landscape, you can ask the following question. Is it better to search far away on the landscape or nearby on the landscape? All right. Anyway, just do a lot of mutations. Let's just use mutation, not recombination now. The general thing's really quite surprising until you think about it. If you're not very good, you will find fitter variants far away faster than you'll find fitter variants nearby, because the variants nearby are constrained by the correlation structure of the landscape. And if you jump far away, you're beyond that correlation length. As the system gets better and better and better, it's better off to look closer and closer to where you already are.
Yeah.
Okay. And that's very, very general. And probably it has something to do with in technology. It's the emergence of lots of variations in bicycles when they're first invented, then the emergence of dominant designs.
Yeah.
So it's very broadly applicable. And just these couple of things to tell you, well, one more thing. Why does recombination work? The best guess is that on modestly correlated landscapes like this one, if you do recombination, in one way or another, if you think of a hypercube, the recombination drops you off on the landscape on a subspace. It's kind of halfway across that space. There's no reason to think that where you're dropped off is better than where you were.
Yeah.
But if this analogy helps, imagine that you're in Europe and you're thinking about the Alps, and you're in Milano and I'm in Zurich. Between us is a landscape that has a correlation structure. It has the property that the higher peaks are near one another. If it's true that the highest peaks are near one another, that if we keep doing recombination, we'll keep being dropped off in the vicinity of ever higher peaks. So we can then hill climb from the higher altitude we are in a better region of the space. That's really why recombination works. I think it's pretty general, Daniel, and it's worth looking into because you guys are talking about using this as a technology, in this case, to find good quantum computer codes that can error correct. So a little time thinking about understanding the structure of the landscape may help the practicalities of your search, because you can only search for 10,000 whatevers. So there's not yet a well worked out theory, you guys, but it seems that we could work out some sort of theory that says sample the landscape, guess its structure, learn more about the structure of the landscape as you go, and use that to tune how you search. I don't know that anybody's done that, but it looks doable. So I'm not questioning you. I'm raising the issues whether you might find this useful.
I totally agree. In what I read about genetic algorithms, not only for many fields, it is an heuristic how you apply crossover and mutations, because normally the structure of the landscape is really hard to map because it has many dimensions. And
sure. That's why the idea is on an n-dimensional space, whatever the space is, just walk randomly. Start somewhere and walk randomly and plot the autocorrelation function.
No, that's really interesting. It's one way of attacking the problem, because when I run my code, I don't just apply the same number of mutations and crossovers. I measure how the populations are walking, if they are changed a lot or not, if I apply mutations. And I adapt the number of mutations that I apply with the past cycles results.
So that would be, Daniel, that would be like when you first start, use a lot of mutations, then tune down the number of mutations. I don't know that this can't be that hard, Daniel.
No, it's not hard.
I don't know that anybody has worked out a way of sampling the landscape as you hill climb, so you know how to hill climb better. That can't be that hard to do.
Yeah.
No, that makes perfect sense. I just want to, I mean, in part, this is why we also wanted you to be here, because you know a lot about this that we don't, right? So you would say you just sample random points in the landscape and try to get the feel for what's the structure, if there is any structure in terms of correlations.
Well, it seems to me that if you just do random points, you don't know anything. There is a good literature on looking at the correlation structure of landscapes. Okay. So just go look that up. And there's decent literature that says if you have a correlation function and it drops off with distance, when it reaches something like 1/e, half the correlation length, that's a tentative measure of the distance between peaks. And suppose you know that. Well, then you know that when you start off, you should jump a long way away with respect to the correlation length. But when you get better, you should jump closer. And there's got to be some way we can figure out when it's a good idea to use recombination and not. I mean, the general result is on really bad landscapes, recombination doesn't help. But what if we are all in the region of high mountains then recombination is going to be a good idea. So how could we find out that we're in a region of high mountains, so recombination's a good idea, then tune the recombination rate? It's got to be possible to do that.